In this video, we return back to our calculus ideas and looking at the derivative, but specifically looking at a new kind of derivative or a new generalization of our earlier derivatives. Recalling what we've seen before, we have already defined the partial derivative with respect to x and the partial derivative with respect to y. And going back to three-dimensional surfaces, if we have a point, we go up to the graph, we can ask what the slope is in the positive x direction, or now we can imagine that in the direction of the vector I. We can also imagine that same calculation defining a slope in the direction of the vector j, which is the direction of positive y in our three-dimensional view. If that's the case, then what we might want to do next is think of going in some other direction. Why are we only talking about slopes in those two cardinal directions? What about in between? What about, a few degrees off of that direction? There is a slope. How are we going to define that? Let's imagine looking at this surface here and trying to find a point where the x derivative is negative. And so remembering what that means, a step in the positive x direction leads to a decrease in the function, and the y slope is positive, then a step in the positive y direction leads to an increase in f. Okay, let's go hunting. So if we imagine a point on the surface, say, let's grab this point here, it's easy to see. Then if we take that down to the plane, if we increase x, then we are definitely decreasing our function. We're going downhill. So that matches this first description here. However, if we take a step in positive y, that would also lead to a decrease in f, and that's not what we want. We want the positive slope when we take a step in the y direction. Okay, well then, knowing what we're missing, if we look at any of the points along here, we can see that a step to the right is going to bring us downwards. That's not going to match the slope that we want in the y direction. So we'd have to go maybe over to somewhere like here. If that's the location we consider, from there, if we increase y, this should be drawn a little more parallel to the axis here. If we increase y there, we will be going up on this hill, so our f is going to increase, and as before, if we take a step in positive x, then we're going to go downhill, and so this point here has the x slope being negative and the y slope being positive. So that's the kind of interpretation we can add to this diagram, interpreting the slopes in those two cardinal directions and finding points that have specific properties. Well, now we're going to generalize. What if we want to go in some other direction? Well, we need to define how we're going to specify a direction. Well, what we can do is define a direction by using a vector. Now, imagine now we're in just the xy plane for a moment. I could define a vector that's like that, a vector like this, a vector like that. Those are a bit confusing in some sense because I just want to know the direction rather than having the magnitude play a role. And so what we're going to enforce when we talk about directions is that we're going to have length 1 only. So all of these length 1 vectors would be comparable, they're on the sort of level playing field, and they have the information we need, which is the direction. Once we have that vector defined, then we want to find the rate of change of our function if we move in that direction away from our reference point. We can take that idea, go back to our diagram, or go back to our graph, and ask ourselves, find a direction, and this is, note here, on the xy plane, where we would find a slope steeper than the fy that we found. Well, if we go back to this point here, it's actually quite clear that it's steeper up this way. Here we're almost at the crest of the hill, it's fairly flat. So if we were to go up something like that direction, that would take us uphill more quickly. Well, that would correspond to a path that's maybe this direction in the xy plane. So that would be a u vector satisfying that property. It's a little murky to see this on the diagram, especially the translation from the surface direction down to the plane direction. But you can certainly see that if we move backwards on this surface, we're going to be going uphill quite quickly, and we can capture that with a direction specified by a vector in x and y. We can also look then for directions maybe where the slope is close to 0. Let's take another look at that point. We're actually pretty close in this red line here. We're going uphill but very shallowly. If we went just a little bit to the side, that would keep us going around this edge here, and that would keep us on a level or flat height. And so we can imagine just going a hair in the positive x direction away from that. That would be a u with close to 0 slope. And the challenge is going to be going forward, noting that the x and y direction is something that we pick that then influences the slope, talking about the surface in relationship to that motion in x and y. So sometimes we'll be talking about just the two variables, the inputs, and sometimes we'll be talking about those two variables along with the consequence for the height of the surface.